Okay, let's jump right into it. Welcome everyone to this deep dive. Today we are tackling a real giant, Sir Isaac Newton, and his whole view of the universe. We're really going to unpack his work, specifically how his scientific breakthroughs laid out the system of the world. We've got our sources ready. We're mostly drawing from Newton's own writing, the system of the world, plus some helpful studies on its impact. Our mission today, it's pretty clear. Pull out the key ideas, the core concepts, and, crucially, the evidence Newton used to build his cosmic system. Let's get into it. So, before Newton, how did people even picture the cosmos? What were the early ideas floating around?
Well, if you go way back, the ancient philosophers, they had some fascinating ideas. Really varied, though. Some believed, the stars were fixed way up high, and below them, the planets and even Earth itself circled the sun.
Oh, interesting. So not everyone thought Earth was the center back then?
Not everyone, no. You find traces of this sun-centered thinking with people like Philolaus, Aristarchus, maybe even the Pythagoreans. Some suggest these ideas might even have roots in early Egyptian observations, philosophy's origins, perhaps.
Huh. But then other ideas took hold, right? The Earth-centered one became more dominant.
Exactly. Later on, thinkers like Anaxagoras, Democritus, they proposed a static Earth at the center, planets revolving around us.
And how did they imagine these things moving, just floating freely?
Well, initially that was often the idea, yeah. Moving freely, no resistance. But then came the concept of solid orbs, these crystalline spheres.
Ah, like the planets were stuck in them.
Kinda, yeah, embedded and carried along. Thinkers like Eudoxus, Aristotle pushed this model. But, comets. Comets were a big problem for solid orbs.
Oh, so.
Well, astronomers like the Chaldeans saw comets as, like planets, but on really weird, eccentric paths. If you have solid spheres, where does a comet go? It would have to smash through them, wouldn't it? Later observations confirmed comets moved at different heights, crossing where these spheres should be. So the solid orbs idea, it had to be abandoned.
Okay, so no solid orbs pushing things around.
Yeah.
Then how do planets curve? Why don't they just fly off straight? That feels like the next big question.
It absolutely was a real puzzle for philosophers. Some, Kepler, Descartes, they proposed these swirling vortices in space, like whirlpools carrying planets.
Vortices.
Others started thinking about some kind of attractive principle. Borelli, Hooke, other English scholars were heading in that direction. The sources are clear. The observed motions had to be driven by some force following mechanical laws. But what's really striking about Newton's approach, you see it in the text, is his focus. He wasn't trying to explain the fundamental nature of the force. What is it? He kind of sidestepped that.
Really? What was his goal then?
Purely mathematical and empirical. Use observations, what you see in the sky, to figure out the strength and direction of the force. Then use math to predict what it does elsewhere. He deliberately avoided getting bogged down in philosophical debates about the force itself.
Just figure out what it does and how strong it is, based on evidence.
Yeah.
Okay. And he gave this force a specific name because of its direction.
Yes, exactly. Since the force consistently points towards a center, the sun, Earth, Jupiter, whatever you call it, centripetal force.
It's center-seeking. Makes sense.
Yep, and you specify which center. The centripetal force around the sun or around the Earth and so on.
Okay, let's dig into the evidence then. How did he show this force exists? The sources use that projectile analogy, which is pretty vivid.
It's a brilliant thought experiment, isn't it? Imagine throwing a stone horizontally off a really high mountain.
Okay.
Gravity pulls it down, so its path curves towards the Earth.
Right, it doesn't go straight.
Now throw it faster, it goes further before hitting the ground, right? The curve is longer.
Yeah, makes sense.
Keep throwing it faster and faster. Imagine eventually you throw it so fast that the curve of its fall matches the curve of the Earth.
Ah, so it just keeps falling,
Okay.
but never hits the ground.
Exactly. If you ignore air resistance, which is basically the case in space,
Yeah.
it would enter orbit. It would just keep going around. And Newton showed mathematically, in Principia, that for an object in such an orbit, the line connecting it to the center sweeps out equal areas in equal times.
Okay, that equal areas and equal times thing sounds important.
It is. It's a key signature of motion under a central force. It shows how a force pulling towards a center keeps something in a curved path.
And there's more immediate proof, too, just from, like, throwing things normally.
Yeah, the sources call it certain proof. Anything you throw, unless it's straight up or down, deviates from a straight line. It curves towards the Earth. That deviation is proof of a force pulling towards Earth's center. It's universal. If something curves towards a point, there's a force pulling it toward that point.
Got it.
how to calculate that force from the curve, or predict the curve from the force. Well, that's the heavy lifting done in the first two books of Principia. The sources also briefly mention, if the Earth didn't move and stars whizzed around us daily, the forces required would be bizarre,
How so?
pointing to weird centers changing constantly. It just doesn't fit observations neatly. The idea of Earth moving simplifies everything dramatically.
Okay, so evidence points to forces directed towards central bodies. What specific astronomical observations nailed this down for the sun and planets?
Several key ones are cited. First, our moon orbiting Earth, its motion sweeping out areas roughly proportional to time.
Slowing down further away, speeding up, closer in?
Exactly. Then you have Jupiter's moons. They orbit Jupiter very regularly, almost perfect circles, very uniform.
Right.
Same for Saturn's moons, regular orbits around Saturn.
Okay.
Then Venus and Mercury, their phases, like our moon's phases.
Showing different amounts lit up.
Yeah, that visually proves they orbit the sun, not the Earth. We see them from different angles relative to the sun. Plus, Mercury's orbit is quite eccentric, and you can see it speed up when it gets closer to the sun. Again, sweeping areas proportional to time.
And Earth itself.
Earth's orbit around the sun fits this pattern perfectly. The radius from the sun to the Earth sweeps areas exactly proportional to time. So you see this consistent pattern across all these different systems. It strongly points to the force being directed right at the center of those bodies.
Okay, this is where it gets really fascinating for me. How does the strength of this force change with distance? Does it get weaker further away?
Yes, and very specifically, this is the huge discovery. The inverse square law. Newton demonstrated that the centripetal force weakens in proportion to the square of the distance from the center.
Inverse square, so double the distance.
Force is 4 times weaker. 1 over 2 squared,
Triple the distance?
9 times weaker. 1 over 3 squared, and so on.
Wow. What was the evidence for that specific relationship?
Really strong evidence came from Jupiter's moons again. Observations showed a precise mathematical relationship. The square of a moon's orbital period was proportional to the cube of its distance from Jupiter.
Okay, period squared proportional to distance cubed, Kepler's third law, right?
Exactly. And that specific relationship is precisely what you mathematically derive if, and only if, the force holding them follows an inverse square law. The source mentions Flamsteed's meticulous observations. His measurements of periods and distances for Jupiter's moons exactly agree with the inverse square law calculations.
So the math lined up perfectly with the observations.
It did. And the same ratio seemed to hold for Saturn's moons, too, though maybe the data wasn't quite as precise then. And for Mercury and Venus orbiting the sun, the best measurements were also consistent with this inverse square relationship.
Okay. Does this same inverse square law apply right here on Earth? The gravity that makes things fall?
Absolutely. And this is maybe Newton's most profound insight connecting the heavens and the Earth with the same law. He reasoned, if the force holding the moon in orbit is the same type of force pulling an apple to the ground, it should follow the same inverse square law.
So he could test that.
Yes. He knew the moon's approximate distance about 60 times Earth's radius and its orbital period, roughly 27.3 days. If the force follows the inverse square law, it should be 60 squared, or 3,600 times weaker out of the moon's distance than it is here on Earth's surface.
Okay, so 3,600 times stronger here.
Right. So he calculated how fast should an object fall in the first second here on Earth if it's subject to a force 3,600 times stronger than the force keeping the moon in its orbit.
Did it match?
Perfectly. The calculated distance matched the experimentally measured distance objects fall in 1 second measurements made accurately using pendulums by scientists like Huygens. The source gives a value like 15 Parisian feet, 1 inch, 1 line.
Wow. So the force holding the moon is literally the same gravity we feel, just weaker because of distance, following that exact inverse square rule.
Precisely. It was stunning confirmation. And this connection holds even when you account for Earth's motion. The moon orbits the Earth-Moon center of mass, pulled by Earth to gravity according to that law. The source says it was most certainly proved.
That's incredible, just unifying celestial and terrestrial physics like that. What else backed up this inverse square idea?
2 things mainly: the shape of planetary orbits and the slow movement of their orientation in space. The orbits are ellipses, not perfect circles. And the points closest and farthest from the sun, the apsides, they shift position very, very slowly over centuries.
Okay. How does that relate?
Newton showed mathematically that if the force deviated even slightly from a perfect inverse square law, those apsides would swing around much, much faster, like noticeably shifting every few orbits.
Ah, I see, but they don't.
Right. For most planets, the movement is incredibly slow. That stability is strong evidence that the force is extremely close to a pure inverse square.
But didn't you say the moon's apsides do move faster?
They do, but that's actually further confirmation. Newton showed the moon's faster apsidal motion is caused by the gravitational pull of the sun perturbing the Earth-Moon system. Once you mathematically account for the sun's interference, the underlying force between Earth and Moon needed to explain the rest of the orbit still comes out as inverse square. The perturbation explains the anomaly.
Clever.
Yeah.
Okay, we have the force, we have the law. How strong is this force for different bodies? Like comparing the sun's pull to Jupiter's pull.
Newton could calculate that too, using the orbital data. The sources show the sun's force is overwhelmingly dominant. For example, comparing the sun's pull on Venus to Jupiter's pull on its own moon at an equivalent distance, the sun's force comes out something like 1,100 times stronger than Jupiter's.
Whoa. Okay, the sun is the heavyweight.
Absolutely. Which also explains why Earth's gravity, while strong to us, is minor on the solar system scale. The fact planets orbit the sun so regularly, despite Earth being nearby, shows the sun's pull is vastly stronger than Earth's. Calculations suggest hundreds of thousands, or at least many thousands, of times stronger, depending on how you compare them.
Okay. What about the planets themselves? Did Newton think they were all, made of the same kind of matter, same density?
Well, the sources discuss measurements of planetary diameters using telescopes. This was tricky back then. Different observers got slightly different results for those tiny disks.
I bet. Hard to measure.
Yeah. But the results hinted at differences in density. And there's this really interesting speculation in the source. Maybe the inner planets, Mercury and Venus, are denser?
Why?
Perhaps because they are closer to the sun, baked more vehemently, as the text puts it, receiving much more heat. Mercury gets like 7 times Earth's summer heat. Maybe their composition, their density, is related to the heat they receive.
And how does density connect back to gravity?
This leads to a crucial idea. The strength of the gravity seems related to the amount of stuff, the quantity of matter in the attracting body. It seemed plausible, maybe even elegantly designed, that the force is proportional to the mass of the sun or Jupiter or Earth. Perhaps denser bodies were placed closer to the sun, fitting the heat, making force proportional to mass the best fit for the system.
So the force depends on the mass of the object doing the pulling. Does it also depend on the mass of the object being pulled?
Yes. Central point. The force acting on a body is also proportional to its mass. The regular motion of moons around planets supports this. The force holding, say, Jupiter's moons must be proportional to the mass of each individual moon for them to orbit as they do.
But how could he test that proportionality on Earth?
The pendulum experiments. Really meticulous work described in the sources. Newton made pendulums with boxes filled with equal weights of different substances: gold, silver, lead, glass, sand, salt, wood, water, wheat, a whole range.
Equal weight, but different materials.
Exactly.
Yeah.
And he found that with incredible precision, all these pendulums, if they were the same length, swung with the exact same period.
What did that prove?
It proved 2 things. First, that an object's quantity of matter, mass, is directly proportional to its weight, the gravitational force pulling it towards Earth. Second, since they all accelerate identically regardless of material, same period means same acceleration, it proved the gravitational force acting on them must be proportional to their quantity of matter. The pull is stronger on more massive objects in just the right proportion to make them fall together.
He checked this very precisely.
Extremely. Down to less than 1 part in 1,000, the source says. Across all sorts of different stuff. Powerful evidence.
Okay, so the force is proportional to the mass of the puller and the mass of the pulled. Both masses matter.
Precisely. Which means the attraction is mutual. It exists between any 2 bodies with mass. And its strength is proportional to the product of both their masses, divided by the square of the distance between them.
Mutual. Like the Earth pulls the apple, but the apple also pulls the Earth.
Yes. Just like a magnet and iron attract each other. It's a single interaction, a mutual pull.
But then, why don't we feel, chairs pulling us, or see mountains pulling things sideways if everything attracts everything else?
Good question. The sources address this directly. Newton actually calculated it. The gravitational pull of everyday objects, even something like a 1-foot sphere made of rock, or even a huge mountain. It's incredibly tiny.
Too small to notice.
Way too small. His calculation for a mountain several miles wide showed it would deflect a pendulum by less than 2 arc minutes. Imperceptible under normal conditions. The effect only becomes significant and obvious when you have planet-sized masses involved, or unless you use incredibly sensitive instruments, which they didn't have then.
Right. Okay, bringing it all together, how does this idea of universal, mutual, mass-dependent, inverse square gravity shake the whole solar system?
It's the architect, really. First, it explains why planets are spheres, more or less. Gravity pulls all their matter towards the center, and the force from a sphere acts predictably inverse square outside it. Second, because the sun's gravity is so incredibly dominant, everything is fundamentally pulled towards the sun.
Unless it's moving sideways fast enough.
Exactly. The fact planets don't fall in proves they are constantly moving, orbiting. Their regular, consistent forward motion shows they orbit the sun. This makes the sun the natural center of the system, the source argues. Its massive gravity dictates the structure, making an Earth-centered model dynamically awkward.
Is the sun perfectly still, though?
Not quite. The true stationary point is the common center of gravity of the whole system, sun and all planets combined. The sun, being so massive, is very close to this point, but it does wobble slightly as the planets orbit and shift the balance point. But it never moves far from the system center.
And the orbits themselves, are they perfect ellipses around this center?
They are ellipses, yes, but orbiting the slightly moving sun. And the equal areas in equal times law is only approximately true relative to the sun because the planets also pull on each other.
Ah, the planetary interactions again.
Right. Those mutual tugs cause small deviations from perfect elliptical paths and perfect area sweeping. Newton noted that if you place the focus of a planet's orbit at the common center of gravity of the relevant bodies, like Earth's focus considering Sun, Mercury, Venus, the math fits better, which supports this model.
And these interactions also explain the slow shifting of the orbits.
Yes, the slow movement of the apsides, closest farthest points, and the nodes, where orbits cross the ecliptic plane. These would be fixed if planets only felt the sun's pull. The fact they move slowly confirms the planets are nudging each other gravitationally. And the source mentions that comets, with their hugely elongated orbits spending most time far out, fit perfectly into this gravitational system, even hinting at the vastness and maybe other bodies beyond Saturn.
Does this framework finally crack the code of the moon's really complicated motion? It always seemed so irregular.
It does. The moon's complexity comes from being caught in a gravitational tug-of-war between the Earth and the much stronger but more distant sun. Newton's work in Principia showed how the sun's perturbing force explains the major lunar inequalities observed by astronomers like Tycho and Horrocks.
Like why it speeds up and slows down relative to the sun.
Exactly. Why it's faster and closer at new full moon, CSTGs, than at quarter moons, quadratures. Why its apogee moves forward and its nodes move backward, and unevenly at that. While nailing down every tiny wiggle was still hard, the main significant variations were shown to be direct consequences of universal gravity, particularly the sun's influence.
And this applies to other moons too. Jupiter's, Saturn's.
Yes, the same principles predict much smaller, slower perturbations for their moons because the sun's influence is weaker out there relative to the planet's gravity, and observations match those predictions.
Okay, orbits, interactions. What about planets spinning? Is that explained too?
Well, gravity doesn't cause the spin, but the spin exists within the system. The sources note that planets like the Sun, Jupiter, Earth, etc. rotate pretty uniformly on their axis relative to the stars. This rotation provides a stable measure of time and isn't affected by the centripetal force pulling the whole planet.
And the moon spins too, right? Since we always see the same face.
Yes, it rotates exactly once on its axis for every orbit it makes around Earth. It's tidally locked. That synchronized rotation, plus its tilted axis, leads to the apparent rocking motion we see, the librations, and as a consequence of spinning. Planets aren't perfect spheres.
Ah, right. They bulge at the equator.
Exactly. They become slightly oblate spheroids due to the centrifugal effect of rotation, wider at the equator, flatter at the poles. For Earth, the sun and moon's gravitational pull on this equatorial bulge is what causes the slow precession of the equinoxes.
The shift in the seasons over millennia.
That's the one. And also nutation, a smaller wobble.
Yeah.
Even Jupiter's equatorial bulge is apparently observable with telescopes. It all fits.
Okay, let's shift focus slightly to something very familiar. The tides. How does Newton's gravity explain the oceans rising and falling?
The tides are a direct result of the differential gravitational pull of the moon and the sun across the Earth, combined with Earth's rotation. The moon, being closer, has the stronger effect. It pulls the water on the side nearest it slightly more strongly than it pulls the center of the Earth.
Okay, creating a bulge towards the moon.
Right, but it also pulls the center of the Earth slightly more strongly than it pulls the water on the far side.
So the Earth gets pulled away from the water on the far side?
Effectively, yes.
Yeah.
Which creates another bulge on the opposite side of the Earth. The sun does the same thing, just less strongly.
Two bulges, and the Earth rotates through them.
Exactly. As your location on Earth spins into a bulge, you get high tide. As it spins out, low tide. Roughly 2 high and 2 low tides per day. And high tide isn't usually right when the moon is overhead, but a bit later, maybe the third hour after, because the water has inertia and takes time to respond.
Got it. And why the big difference between spring tides and neap tides?
That depends on how the sun and moon line up. Spring tides, the highest high tides and lowest low tides, happen at new and full moon. That's when the sun, earth, and moon are aligned.
So their gravitational pulls add together.
Precisely. They combine to make the biggest bulges. Neap tides, the less extreme ones, happen at the quarter moons when the sun and moon are at right angles relative to Earth.
Pulling in different directions.
Yeah, so their forces partially cancel each other out, leading to smaller tidal bulges. The moon's effect dominates the timing, though, because its pull is stronger. Other things affect height, too, like distance.
Closer moon or sun means higher tides.
Yes, the force depends on distance. So tides are slightly higher when the moon is at perigee, closest, or when Earth is closest to the sun in northern hemisphere winter. Also, declination matters. Tides tend to be largest near the equinoxes when sun and moon are near the celestial equator.
What about those strange places with only one tide a day, or really weird patterns?
Yeah, the source mentions places like Belchaport in Tonkin. That's usually due to local geography and how the tidal wave interacts with coastlines and basins. Away from the equator, the two daily high tides can be unequal heights. In some places, complex interference between tidal waves arriving through different channels can cancel out one tide, especially when the moon is far north or south.
And local shapes matter a lot. Bays and channels.
Hugely. Narrow straits, shallow rivers, funnel-shaped bays, they can dramatically slow down and amplify the tide. High tide can be hours later inland than on the coast. And places like the Bay of Fundy, or Mont Saint-Michel mentioned in the source, funnel the water to create enormous tidal ranges, 40, 50 feet or more. It's interesting, Newton calculated the actual direct force difference causing tides is tiny.
How tiny?
Like the sun's differential pull is only about 1/12 millionth of Earth's surface gravity. Even sun and moon combined at spring tide is only about 1/2 millionth.
But the tides are obviously much bigger than that implies. A few inches wouldn't explain 50 feet.
Exactly. That's where the reciprocating force comes in the water's inertia. Once the gravitational pull gets the vast ocean water moving, its momentum carries it much further, amplifying the effect like water sloshing in a huge basin. By comparing the observed heights of spring and neap tides, like 45 feet versus 25 feet in Bristol, Newton estimated the moon's tide-raising force as roughly 4 times the sun's.
So you can work backwards from the effect?
Right. These forces are too small to detect with scales or pendulums, but they move oceans. He even used tidal effects to estimate densities, suggesting the moon is denser than Earth, which is actually the opposite of modern values, but the reasoning process was there.
Okay, so gravity covers the solar system, Earth, moon, tides. What about the stars? Way out there.
Stars are just fundamentally different in scale. Newton knew they were incredibly far away because they showed virtually no annual parallax.
No shift in apparent position as Earth orbits the sun.
Almost none detectable back then. Less than an arc minute. That meant they had to be hundreds, probably thousands of times further away than Saturn. He also used a brightness argument. If our sun were moved out to stellar distances, say 100,000 times Saturn's distance, it would look about as bright as a typical star.
So stars are likely other suns, just incredibly distant.
That was the conclusion. And he argued against light being significantly absorbed in space, because that wouldn't fit the observed brightness of distant stars either. So the bottom line, stars are so far away that their gravity doesn't really affect our solar system, and our sun's gravity doesn't really affect them. They're effectively separate gravitational domains.
Okay, makes sense. One last piece. Comets. They just appear, wander across the sky. Are they part of this gravitational system too?
Definitely. Newton was quite clear. Comets obey the sun's gravity. The evidence showed they weren't random visitors from interstellar space, nor were they atmospheric phenomena.
What was the evidence?
Well, first, they lacked diurnal parallax. They didn't shift position noticeably when viewed from different places on Earth simultaneously. That meant they were further away than the moon.
Okay, beyond the moon.
But crucially, they did show annual parallax. Their position shifted against the background stars over months due to Earth's own orbital motion.
Yeah.
That proved they were within the planetary region orbiting the sun.
Ah, so their apparent strange motion was just parallax.
Largely, yes. They're slowing down, speeding up, even moving backwards sometimes. That was mostly an effect of our own changing viewpoint as Earth moved. Astronomers found their paths were actually regular curves, ellipses, or maybe parabolas centered on the sun. Some came very close, even inside Mercury's orbit. Their brightness also suggested they were closer than stars. Some got as bright as planets.
So comets aren't weird anomalies. They're just other members of the solar system following the same gravitational rules, but on much more elongated paths.
Exactly. They fit perfectly within the system governed by universal gravitation.
Wow, okay. So we've really covered a lot of ground. From ancient ideas of, fixed spheres through Newton's meticulous work showing this single principle universal gravity connects everything. Falling stones, orbiting moons, the shape of planets, the rhythm of tides, the paths of comets, all explained by this one inverse square law proportional to mass. It's truly a unified system of the world.
It really is. This deep dive into Newton's own arguments, it just paints such a clear picture of a universe operating under elegant, discoverable mathematical laws. A universe where, the force we feel right here extends out across vast distances, linking everything in this incredibly intricate gravitational dance.
So hopefully you listening have got a much clearer picture now of the mechanics Newton brought to light.
And think about this. Newton laid out this incredible clockwork universe, explaining so much with such precision. But even he noted small irregularities, things that were hard to perfectly pin down back then. It makes you wonder, doesn't it? Is the universe entirely predictable, a perfect machine governed by these laws? Or are there always deeper complexities, things just beyond our current grasp?
That's a great thought to leave things on. What does this journey into Newton's system make you think about the universe and where science might go next?
Thank you for joining us for this deep dive.
See you next time.